So, somewhat early, but most of the people who are going to come are probably here. Pleasure to have Phil Reny, who's going to give a distinguished visitor lecture. Another long title.
Thank you, Peter. Thank you, Peter. Henang, thank you for the invitation. Yi Chun, thank you for the invitation. Great to be here. So Roger and I have been, Meyerson, my co-author, and we've been working on this for a long time. 10 years probably, I think. We've tried. I checked my email, and the first email that I can find between Roger and me on this topic is something like 2008. So Roger thinks we've been doing it for longer, but that's as long as I'm willing to admit. So 10 years. So why has it taken so long? You know, this problem's been around we could say for 35 years, since 1982, since Krebs and Wilson defined sequential equilibrium for finite games. You open, any journal that includes some theoretical papers, Econometrica, Restud, AER even. You'll find extensive form games with infinite actions and infinitely many information sets and signals and game theory is being done in these extensive form games somehow. And of course, concepts like perfect Bayesian equilibrium, various versions of them, what do you do in subgames, one has to say. And so, we need some methodology for analyzing these games, and that's the intention of this project. So we should probably start just by reminding ourselves, what is a sequential equilibrium in a finite game? And it's a pair. It's a behavioral strategy profile, so a behavioral strategy for each player in the game, and a system of beliefs. They have to set that pair has to satisfy two properties. It has to be sequentially rational and consistent. So what does it mean to be sequentially rational? It means that at each of your information sets, your belief there, what's a belief for you? It's a probability distribution over the histories of play that you can't distinguish between. So given your beliefs about the history of play, and given the strategies of the others that they're going to use in the future, your strategy maximizes your conditional expected utility. Okay, that's true for each player at each information set. So that's what it means to be sequentially rational. What does it mean for this assessment, this pair, to be consistent? The beliefs have to have some consistent relation with the strategy profile. One obvious consistency property is Bayes' rule. Any information set that's reached with positive probability, the beliefs there should be those determined by Bayes' rule. So always the issue is, well, what about the off equilibrium path information sets? What should the beliefs satisfy there? And there are a variety of conditions that seem very natural that one would want to impose. And Krebs and Wilson combined all of those natural conditions into one technical condition that included all of those and perhaps many, many more conditions. But what was the technical condition? Well, they said the pair, or the system of belief, let's say, is consistent with a strategy profile. If there is a completely mixed strategy sequence of completely mixed strategy profiles converging to the strategy profile in question, such that the Bayes rule-induced beliefs along the sequence converge to the beliefs at the system of beliefs at the information set. So, the beliefs that you hold should be nearby to Bayes rule-induced beliefs that come from nearby strategy profiles. Okay, that's what it means for the assessment to be consistent. Okay, so that's sequential equilibrium in finite games. What's the problem with games with infinite actions and infinitely many information sets? A basic problem is if you have, in general, let you say, a continuum of actions, continuum of information sets, it's not going to be possible to give a strictly mixed strategy. I mean, in a finite game, it gives all information sets positive probability, which is very convenient for the consistency condition. It's impossible, of course, to give a continuum of disjoint events, so here information sets positive probability at the same time. So that's a basic problem. You might, and indeed Roger and I don't know, maybe for 5 years, I don't know how long, too long, embarrassingly long, spent a long time thinking, the obvious solution, of course, to a problem whose solution we know in a finite case, whatever that mathematical problem is, how to extend the finite to the infinite. Of course, you take limits. Whatever infinite object you have, you approximate it with an appropriate finite object, use the finite solution and take limits. Of course, that's what one should do. And we went down that road for a very long time until at some point down that road we realized, here's an example. We had this, what we thought was a great solution, a finite approximation of infinite games and take limits. And we realized, wait a second, that actually there are examples of infinite games where when we use our finite approximation, we're getting answers that intuitively, to our sense, subjective sense, we're getting the wrong answer, an obviously wrong answer. So that approximation was no good. Okay, so we went back to the drawing board, tried to fix up the way we were approximating infinite games by finite games, and great, we were very happy for a while. And then again, an example showed up, and darn it, no, that method of approximation is also terrible, because in this class of these examples, you're getting an obviously wrong answer. No one would accept that as a sequential equilibrium to this infinite game. And we went on like that for a little while, and then we just realized we don't know how. We have no clue how to approximate in a general infinite. A game with infinite actions and infinite information sets by a finite game. So if any of you can figure out how to do that, that would be a great method. We just couldn't figure out how to do it, and so we abandoned that approach. And if there's time, there probably won't be, but I can talk about one particular example that shows you that you get into trouble trying to approximate that infinite game with a finite game. So we abandoned that approach, which means we really have to deal with the infinite game directly. Okay, and once you deal with the infinite game directly, you're going to have several problems. One is you have to come up with now a new definition, because you can't use Krebs and Wilson. At least it's not obvious how to do it, because it's not a finite game. Second, the issue of existence is going to be a real issue. Existence of whatever solution you define, now you have infinite objects, and existence is going to be a challenge. So it was with a lot of hesitation that we went this route. We felt we were forced to. Okay, so that's somewhat by way of long introduction. Let me now show you, let me start with an example that will show you that, conditional on going that route, that have to deal with the infinite game itself, come up with some kind of generalization of sequential equilibrium, what problem you run into right away. So again, let's remind ourselves, so Krebs and Wilson, the basic idea, and again, let me say, there are two components to sequential equilibrium. There's the sequential rationality and the consistency component. Sequential rationality, no problem to extend that to infinite games. If you have behavioral strategy profiles, you can define systems of beliefs if you want to, and you can say it's obvious how you would define sequential rationality. So that's not the problem. The problem is the consistency part. Okay? Now, the whole objective of, so let me before going that, let me say that one could actually define in finite games sequential equilibrium without introducing beliefs at all. So if what you're interested ultimately is the strategy profile, the sequential equilibrium strategy profile, in fact, you can define sequential equilibrium strategy profiles without talking about beliefs at all. And I'll write down a definition. So a strategy profile, say B, so there are n players. Strategy profile is a sequential equilibrium, part of what I'm just going to call it a sequential equilibrium, if and only if, for every positive epsilon, there is a completely mixed strategy profile, call it B prime, and that's arbitrarily close to B. So if you want to think of a sequence, you can, but there's a completely mixed strategy profile that's arbitrarily close to B, such that if we think about using that strategy profile, so under the strategy profile B prime, every player is epsilon optimizing, so conditional on each of their information sets. So I'll just say every information set. Okay, so you could check whether or not a strategy profile is a sequential equilibrium. How do you check? If for every epsilon, you can perturb the strategy profile arbitrarily, slightly, such that that perturbation is completely mixed, and now conditional on every information set, under that perturbation, the players are epsilon optimizing. The original strategy profile was a sequential equilibrium. And you kind of see how that's working. This perturbation is playing the role of the completely mixed strategy that's converging. Because we're conditioning using this completely mixed strategy, we're doing, of course, the Bayes rule-induced beliefs, and we're epsilon optimizing, and so in the limit, we're going to be exactly optimal. So you get everything, and it goes both ways. Okay? And so to make our lives going to the infinite is hard enough. This is what we're going to try to generalize. Okay? We're going to try to take that definition where we can put the beliefs in the background and not really, we don't have to be explicit about the beliefs at all. And we want to generalize this take that definition and bring it to infinite games. Okay? So, but the problem is the completely mixed. Yes, giving every information set positive probability, that's going to be a problem when you have a continuum of disjoint information sets, which one often does in infinite games. But what you could do, the purpose of the perturbation is really to give every information set positive probability. And while you can't do that with one perturbation, what you could do is look at, finite collections of information sets and perturb to give any information set in the each information set in the finite collection positive probability, and check that players are epsilon optimizing given those perturbations. Okay, so that's sort of the rough idea. That sounds pretty good. That's doable, and maybe it would produce good results. But let's look at this example in that context. Okay, so what's the problem with that? The problem of trying to test, the purpose of the perturbations to give information sets that have probability 0, positive probability. What's the purpose? The purpose of that is for the benefit of players early in the game, testing whether or not what's going on in the future that's actually, rational. What's going on there, I should believe what's happening there is really going to happen, even if I probe if I deviate, and maybe a sequence of deviations would have reached that information set. This is how one tests to make sure in the theory that actually rational behavior is happening everywhere in the tree, even off the path. That's the purpose of the perturbations. Okay, so that's what we want to do. So what's the problem of testing, so-called conditional rationality, let's say, with positive probability in all events. Okay, so here's a game. Nature is going to choose two coordinates. So nature is theta. She has two coordinates, theta 1, theta 2. One of them will be discrete. Theta 1 is either 1 or 2. And it has probability, 1 has probability 1/3 and 2 has probability 2/3. So theta 1 is either 1 or 2. 1/3, 2/3. And theta 2 is uniform 0, 1. Okay, so two coordinates. One of them is discrete, first coordinate. Second coordinate chosen uniform 0, 1. And that's chosen at date 1. Player 1 chooses x, a real number between 0 and 1. So all of this happens at date 1 simultaneously. Date 2, now player 2 is going to observe a real number. Now notice there are two real numbers that were chosen at date 1. One of the real numbers was chosen by nature, her second coordinate. The other real number between 0 and 1 was chosen by player 1. Player 2 on date 2 is going to observe either nature's choice of real number or player 1's choice of real number, depending on whether nature's discrete coordinate, theta 1, was 1 or 2. Okay? If it was 1, player 2 is going to observe player 1's choice of real number. If theta 1 was 2, then player 2 signal is going to observe player 2's choice of real number. Okay? So maybe a picture might help. It might not, but it might. So let's see. Let's see. Nature starts, chooses either, and it'll look like it's not quite date 1 and date 2, but bear with me. Let's see. Theta 1 equals 1. Theta 1 equals 2. So this is probability 2/3. Probability 1/3. If theta 1 is 1, if theta 1 is 1, I'm not quite drawing exactly in the because it would be too big and the irrelevant details would be sitting around. Let me just write it this way. So then, if theta 1 is 1, player 1 is going to choose a number between 0 and 1. If theta 1 is 2, then what matters is nature's choice of real number. It matters only if theta 1 equals 2. So then nature chooses here a number. This will eventually look okay, I hope. So here's player 2's choice. Okay, so this number here is x between 0 and 1. And this number is theta 2. Also between 0 and 1. And player 2 doesn't know whether the number that was chosen was the x or the theta 2, and that depends on whether it was theta 1 or theta 1 is equal to 1 or 2. Okay, so player 2 is going to choose y, either 1 or 2. I don't know if I'm there yet. Yes, I am. Okay, so that's this game. Again, more or less, given the simultaneity that I've stated up top here. What are the payoffs? Let's start with player 1. Well, let's just first look. Notice the payoffs here depend only on player 2's choice of y and nature's first coordinate choice of 1 or 2. So nature's, the continuous variables, the theta 2 and the x, play no role in the payoffs. So player 1's choice of x and nature's second coordinate play no role in the payoffs. But let's see what the payoffs are here. Notice that player 1 gets a payoff of 1 no matter what theta 1 is, so long as player 2 chooses 1. And player 1 gets a payoff of 0 if player 2 chooses 2. So player 1 just wants player 2 to choose 1. Okay? No matter what. What about player 2? Player 2 would like to match the first coordinate of the state. So if the first coordinate of the state is 1, player 2 gets a payoff of 1 if she chooses 1. She gets a payoff of 0 if she chooses 2. If the first coordinate of the state is 2, player 2 gets a payoff of 0 if she chooses 1, and 1 if she chooses 2. So player 2, yes, her choice of 1 or 2 here, she would like to match the first coordinate of 1 or 2. All right? Now notice that the prior on theta 1 is 1/3, 2/3 on 1 and 2. So if player 2 gets no information about theta 1, then of course she's going to choose 2. Yes, it gets 2/3 in expectation versus 1/3. Okay? Now, there are lots of sort of sensible equilibria of this. This is not a particularly hard game to sort of decide what should be the right answers. So for example, one reasonable sounding sequential equilibrium, if we knew what that was in this game, would be, say that, player 1, nature here is uniform 0, 1. So let's just make player 1 uniform 0, 1. And then player 2, when she sees a number, it really doesn't matter which number she sees. She knows both of them are uniform 0, 1. It gives her no information about theta 1, theta 2. So she chooses y equals 2, no matter what number she sees. And given that she's choosing y equals 2 no matter what number she sees, player 1, can't do a darn thing about it. Might as well randomize uniformly over here, and that seems like it's just fine. Okay? And there are plenty of just fine equilibria like that, and there are a continuum of them, and I won't, Though there are others. So for example, player 1 could, with probability 1, choose x equals a half. Let's just talk about that one. If player 1, whenever he gets to move, chooses x equal a half, then, x equals a half has positive probability, and that happens with probability a third, that will happen. So player 2, when she sees x equals a half, she will know, this must have happened. It must be state 1, so I will play y equals 1 when I see x equals a half. But if anything else, I'll know we were over here, and I'll choose y equals 2. That's also a perfectly fine equilibrium, and you can start making, you can see how you could construct other such nice equilibria that you might want to call sequential equilibria. Okay? Okay. What's the problem? So again, this game in and of itself is not a problem. I mean, for us to intuitively decide what the right answer should be. But in proposing a theory that's trying to capture this idea somehow. So suppose you try to capture that idea in general by saying, okay, give me any finite number of information sets in the game. Let's perturb the player's strategies to give those information sets positive probability and check that we've got, sequentially rational behavior there, given those perturbations. Well, what would happen here? Let's suppose, let's take the signal 1/2 for player 2. That's an information set. Yes, a signal of a half. When she gets that signal, she can't distinguish between whether it was that nature chose theta 1 equals 1 and player 1 chose a half, or nature chose theta 1 equals 2 and theta 2 equals a half. She can't distinguish between those two histories. So that signal, the inverse image of that signal, right, the set of histories, is an information set for her. So, well, let's perturb the strategies. Suppose that we have some. Let's take the uniform distribution equilibrium. Let's suppose that information set is probability 0. Let's perturb the player 1 strategy here to give that information set positive probability. So if we perturb player 1's strategy to give, let's make this a half right here, x equals a half, to give this positive probability, then certainly when player 2 sees a half under that perturbation, she's going to say, aha, it must have been. This has probability 0. It must be that her beliefs here, if we had beliefs, would be 1 and 0. She'd know for sure she was over here under that perturbation, which means that she's going to choose y equals 1 with probability 1. That's the only rational thing to do for her. And if we do that for every, we have any finite set of information sets, let's say we're going to perturb and check the rationality of the players under that perturbation, that would say that, the conclusion would be that we could do that for every signal. Player 2 should choose y equals 1 no matter what. That's the conclusion we would draw. But of course, in this game, choosing y equals 1 no matter what is strictly dominated by choosing y equals 2 no matter what for player 2. Okay, so you just get non-existence here of a sort of rational solution. So that's a problem. But there's kind of an obvious answer. The obvious answer, I think there's an obvious, the obvious answer is, why is it the problem is that when you perturb player 1's strategy here, you're kind of biasing 2's beliefs away from probability 0 events for nature. I mean, you know, when you have a continuum of choices, say for nature, some of them most of them have to have probability 0. Okay, it doesn't mean they're impossible. Certainly doesn't mean that players shouldn't believe that, you know, nature did something. And when you're talking about out of equilibrium play and out of equilibrium beliefs, you know, it's fair for players to think, well, yes, this history would require a probability 0 event for nature. On the other hand, this history would require perhaps a deviation by some player. And now one has to weigh the relative likelihood, subjectively or somehow, of this probability 0 event for nature and this deviation by a player. There's no reason it should always come out that the deviation by the player is infinitely more likely than the probability 0 choice of nature. Why should it? Okay? So to avoid that kind of bias and to continue with the perturbation idea, you can't just perturb the players, you have to also perturb nature. Okay? I want to emphasize, we use the word perturb, and we often also talk about trembling hand perfection and mistake probability. Nature is, you know, nature's not big. Nature doesn't make mistakes. Okay, so if we were to perturb here nature's strategy to give some mass on a half, that's just capturing the idea that player 2, when she sees a half, says, you know, it could be that 1 did this and that, and it could be that nature did this and this. Okay? There's nothing in what player 2 is thinking that suggests that nature made some kind of mistake. Okay? So perturbations are not equivalent to mistakes. Even perturbations of the player's strategies don't mean players are making mistakes. It's just a way to capture the beliefs of those who are in a position of thinking, what happened? How did we get here? Okay, so that's coming. So you know, in finite games, and the finite games that Krebs and Wilson studied, they made sure, when they wrote you'll see, they made sure, we're going to focus attention only on games where all of the finite states of nature happen with strictly positive probability. They avoided this problem. In that case, perturbing nature has no effect. You can perturb both nature and the players. You might as well just perturb the players, because the positive probability states swamp the tiny perturbations that you might do for nature anyway, okay? So in some sense, you could say that Krebs and Wilson already, you know, they perturbed nature, you just couldn't tell. Okay. Okay, so let me give you just now the class of games that we study. These would be multi-stage games. So play occurs in a finite sequence of dates. One could take in infinite dates. It's just more notation, and that's not the point of the exercise yet at this point. So what happens at a date? At date t, nature is going to choose, so 0 subscript will be nature. So nature chooses A0t at date t out of her action set according to some probability distribution, which can depend on the entire history of play. So A sub less than t means the entire history of play up to that point, including nature. So all of the players and nature. Also at date t, the players, I guess I used n over here, but it's capital I actually in the paper, privately observe a signal. We'll say where those come from in a moment. It's called SIT. So player I at date t observes a signal, SIT, and then chooses an action from his action set A sub IT. We can talk about allowing action sets to depend on the histories, but no right now. Where do these signals come from? Well, there's a map. A mapping sigma IT takes a history, any history of play, and maps that into a signal for you, player I at date t, and for each of you, player I's at date t. So for example, if that signal map was a constant, it would mean that you know nothing about the history of play, because you get the same information no matter what is the history. If that signal map was the identity function, you'd have perfect information about the history of play, and you can have anything in between. In general, given your signal, the inverse image of that signal under the signal map, what is that? That's the set of histories that generate that signal. That's an information set. The set of histories you can't distinguish between. Okay, so the word signal for us means information set once you combine it with the signal map. The inverse image of the signal under the signal map is a set of histories you can't distinguish between. Okay. So an outcome of the game is just a product of all of the action spaces, including nature. Players have bounded, the measurable. And by the way, there's measurability stuff all over. I'm just not mentioning it. Bounded utility, bounded utility function. What's a strategy? A strategy is a mapping. Again, it's going to be a transition probability. So there's measurability properties that one would want. BIT maps a signal, SIT, into a probability distribution over action. So it's a behavioral strategy for player I at date T. And of course, a strategy for a player I is just stringing together all of her date T strategies for all dates. And a profile is just a combination of all of those things, B1 up to BI. So let me do it right here. Okay. Okay, that's that notation which we had to do. An important idea is optimizing conditional on an information set that has positive probability, and so I want to talk about a concept that we'll call conditional epsilon equilibrium. By the way, epsilons are appearing, and they'll kind of go away eventually, but in terms of optimization, again, the infinite game case introduces complications. In general, and again, there are examples, very nice examples, of simple games with infinite actions, really nice games. So just two-stage games, 2 players in each stage, playing simultaneously. In the first stage, their actions, no nature. The players' actions are revealed to the 2 players in the second stage. Everything's compact, continuous payoff functions. No subgame perfect equilibrium. Okay, there are examples like that. You just would think that can't be possible, but it is. Okay, so a situation like that, a stage game, simultaneous play, actions are revealed, simultaneous play. What's a sequential equilibrium? It's just subgame perfection. But there are examples where no subgame perfect equilibrium exists, even when everything is compact, continuous, beautiful. So one can't hope, to get exact equilibria. That's why the epsilon is here. Okay? So, conditional epsilon equilibrium, what is it? Well, let's first talk about continuation strategies. It's what you would think. If we start with player I and a strategy profile for player I, a date T continuation strategy, what is a CI? What is it? It's just, it's the same strategy up to date T and maybe different at date T and afterward. Okay, so it's equal to BI for all dates less than T. That's a date T continuation. So what's a conditional epsilon equilibrium? It's exactly what you think it should be. It's a strategy profile B with the property that for every player I, for every date T, and for every set of signals that has positive probability, for every set of signals, again, set means measurable set, that has positive probability under the strategy profile, conditional on that set of signals, you're epsilon optimizing. That is, the payoff you're getting at B, well, you can't improve on that remember, you're at date T here, okay? So where are we? We're at date T. These are signals that you observe in date T. You can't improve conditional on being with this signals at date T. You can't improve your payoff by more than epsilon for any date T continuation. Okay, so that's what it means to, and if that's true for all dates T, all date T continuations, then we say that B is a conditional epsilon equilibrium. Okay, now we're only here checking, of course, at a set of information sets, subsets of sets of information sets that occur with positive probability. Okay, so of course there's lots that one needs to do to get to sequential equilibrium here. But that's a basic idea, conditional epsilon equilibrium. Is that okay? Okay. So one thing you might think of doing, you know, because of the problem of just perturbing the strategies, perhaps you don't want to perturb nature. See, you know, maybe there's another route. Instead of perturbing nature, another route might be, and a very natural one, is to introduce topologies somewhere, maybe on the player's actions, maybe on signal spaces somewhere, and talk about giving positive probability to all of the open sets. So you make things separable some way. You have a finite collection. You have a countably generated set of open sets, and you can give every open set's positive probability with a single strategy profile. That, you know, hey, that sounds pretty good. So let's think about that. What about that? So let me give you an example. Player 1 at date 1 chooses a number x between 0 and 1, a real number, any real number between 0 and 1. Player 2, you'll be player, so I'll be player 1. I choose a real number between 0 and 1. You, player 2, you're going to observe the number. Actually, half of you over here will be player 2. You'll observe the real number that I choose, and then you get to also choose a real number between 0 and 1. Okay, good. Then there's nature. Nature is just on, let's say on date 3, we'll choose either a -1 or +1, a discrete variable, with half, equally likely half-half. And then player 3 comes in over here. Player 3, you observe something. What do you observe? You observe the product of nature's choice, -1 or 1, and the sum of our choices, x plus y. Okay? So you observe theta times x plus y. And then you choose either -1 or 1, -1 or +1. Okay, so that's the game. Well, we have to, what are the payoffs? The two of us, players 1 and 2, we have common interests. What are they? Well, theta is nature, z is the choice of player 3. And those theta and z are each either 1 or -1. We would like those numbers to be opposite one another. Okay, we would like player 3 not to coordinate with nature. But of course, player 3 has the opposite preferences. She would like to coordinate with nature. She would like z to be equal to theta. Okay, to get a payoff of +1 rather than -1. So we would like to conspire, if we could, to make sure that player 3 cannot match nature. Player 3 would like to match nature if she can. Good. That's what this says. So now we can prevent, notice, look at player 3's, let's take a look at here. Notice that if this sum is positive, x plus y, if that's positive, you know, theta is either -1 or +1. So this number, S3, will be either negative or positive, yes? If this is positive number, then this will be negative. If and only if theta is -1, it'll be positive. If and only if theta is +1. Okay? And, you know, its absolute value will not be 0 as well. So if x plus y is positive, then if player 3 is going to be able to figure out what the state is by looking at the sign of her signal. The sign of her signal tells her what the state is. And then she can match the state, which is bad for us. We don't want her to be able to match the state. How can we prevent her from matching the state? Well, if we both chose 0, I choose 0, you choose 0, then she observes 0. And so she doesn't get any information about the sign of the state. And so she can't match the state. So you and I can prevent her from player 3 from matching the state if we both choose x equals y equals 0. And so because you observe my choice, I choose x first, you then observe my x, and you choose y. If I choose x equal, of course, if I choose a positive number, nothing you can do. This is going to be positive, and we're in trouble. But if I choose x equals 0, then you know, player 2, that if you choose y equals 0, then we've succeeded in preventing player 3 to discern the state, and that's good for us. So in any subgame perfect equilibria, x equals y equals 0. Okay, good. And we get a expected payoff of 0, which is the best we can do. But with this topological approach. So suppose we think about, what does it full support mean here? Full support would mean that suppose we just insist that you know, if we're going to perturb strategies, it's good enough in terms of perturbing to give every open set of my action space positive probability, and you giving every open set of your action space positive. That's what we mean by perturbing the strategies. And if we check rationality conditional on strategies that give everything, all the open sets positive probability, that's kind of what we should mean by a sequential equilibrium, maybe limits of those things. Okay? Well, here's no, we're in trouble. Consider the following strategies. Suppose I choose uniform, my x uniformly, 0, 1. Dumb thing to do, of course. And you choose your y uniformly. Okay, so that's our strategy. I choose my x uniformly, you choose your y uniformly. And you know, player 3 does the rational thing. If she sees a positive signal, she chooses z equals 1. A negative signal, she chooses z equals -1. So she's. I claim that, you know, conditional on every open set. So if that's what we mean by checking rationality in the topological approach, conditional on every open set, and all that matters here is you. Notice I'm optimizing, because if I think you're choosing uniform 0, 1, no matter what you see, with probability 1, player 3 is going to be able to figure out the state, and nothing I can do about it. What about you? Are you optimizing conditional on every open set? Yes, you are. Okay, because conditional on every open set of signals for you, the signal 0 has probability 0. And so when you condition on every open set, because the signal 0 has probability 0, my x has probability equals 0 has probability 0, you know, with probability 1 conditional on any such set, that my x was positive, and player 3 is going to figure out the state. So you might as well choose uniformly. Okay, so this strategy profile has the property that conditional on every open set, every player is optimizing. And yet it's a crazy equilibrium. It's not subgame perfect even in this game. So the property that conditional on every open set, every player is, and every open set has positive probability in the game, and conditional on every open set, every player is epsilon optimizing, in fact, fully optimizing in this example, it's not good enough. It's not good enough a test, even though we're testing behavior at every open set, each of which has positive probability. We're not testing behavior at the crucial point, which is the signal 0 for you. That's the crucial signal in this game, and that if we just, it's not an open set. Now, of course, you could say to yourself, you know, that signal, actually, now that I think about it, that signal is a really important signal. We should just define that topology, make that a discrete point an open set. I mean, we can't do game theory that way, right? We can't sort of first solve the game, figure out then what the, you know, I can come up with all kinds of examples that would make that exercise very complicated, okay? So this approach, it's just, so the moral of this example, okay, is that you really have to check every signal itself. And to do that, you have to perturb the game in a way that you can give every signal positive probability. And then you have to worry about biasing the beliefs if you choose not to also perturb nature. Okay, so putting all that together, we were led eventually 10 years later, you know, to perturbing both the players' strategies and nature. And that's the only way we can see how to do it, and not to say there aren't ways that you could see that would be better, but okay. So just now in words, how am I going to eventually, very shortly, define what I mean by a perfect conditional epsilon equilibrium. So here we know what a conditional epsilon equilibrium is, but it might not be perfect because it may not be testing rationality everywhere off path. We're only testing rationality at events that have positive probability. To be perfect, we have to test rationality everywhere. So how to do that? So it's a perfect conditional epsilon equilibrium. If given any finite set of signals in the game, in the entire game, any finite set of signals, so for any number of players, dates, wherever, give me a finite set of signals. And now here, outside some negligible sets, I'll define what the negligible sets, well, we can ignore by definition. Yes, they're negligible, but we'll get to what that means in a moment. So given any finite set of signals outside a negligible set, we must be able to perturb the player's strategies and nature's probability function, so perturb the players and nature, arbitrarily slightly, so that every signal in the finite set has positive probability, and so that the perturbed strategy profile is a conditional epsilon equilibrium in the game with nature's perturbed probability function. Okay? So in other words, under the perturbation, what is the perturbation? We're perturbing the players and nature. So under that perturbation, and nature's probability function, the perturbed strategy profile is a conditional epsilon equilibrium. Okay? So it's really this exactly, except in addition to perturbing the player's strategies, we're perturbing nature's strategies. That's one change. The other change is we're not talking, I don't know what this means in an infinite game, but the purpose of this is to give every information set positive probability, which of course I can't do. What I'm doing instead is, well, you give me any finite set of information sets, signals here. I will test those, and I'm going to pass the test. Okay? Now, we could have said here in the definition, give me any countable set of signals. Let me just add. We would also get an existence. Everything would go through, but we couldn't, I can't, maybe you can. We couldn't find an example where that made any real difference. Okay? And so it just seemed, it's a nicer definition. And so we left it at that. Okay? It would be in principle a stronger definition, say countable, but good. Okay. Okay, so those are the words. Let's put some formality to the words. So there are the words again, same words. So there are two pieces, several pieces. What do I mean by a negligible set of signals? What's a negligible set? It's really what you think it should mean. So take a player I at a date t. And these are the measurable sets of signals for that player. So take any measurable set of signals for player I at date t. We'll call it negligible. If that set of signals has probability 0, no matter what strategies the players play, no matter what strategy profile is in effect. So for example, if nature moves first, choosing uniform 0, 1, and you observe nature, and then other stuff happens after that. But let's just take that. Nature moves first, chooses a random variable, uniform 0, 1, and you observe the outcome of that, nature. Okay? So any Lebesgue measure 0 set of nature's choices is a negligible set of signals for you. Okay? And if that happened deeper in the tree, that you observed nature at that stage, and I'm thinking about, how are you behaving? Are you behaving rationally there? There's nothing I can do and suppose you're behaving irrationally, let's say, on a set of Lebesgue, after the set of Lebesgue measure 0 that you might observe. You're behaving crazy. Well, there's nothing I can do that would ever make those events, that I would ever care about what you're doing there. So if everything else in the tree in the game is just, beautiful in terms of rational play, the fact that you're doing something silly on that negligible set, it's not going to affect anything. We could change what you do and make it rational there, but again, wouldn't affect anything for anybody. Okay? So we really don't have to check signals outside a negligible set. Good. Let's take the disjoint union, let's say, of all the signals. So now we have a notation for the set of all signals in the game. And so we can say a subset of signals in the game is negligible if the intersection of that with each player's signals at any date t is negligible. Okay. Okay, so those are negligible sets of signals. What else do we have to think about? What does it mean to perturb the player's strategies and nature's probability function? What do we mean by a perturbation of a strategy profile? Well, again, it's what you would think. So nature's probability function is P, and C is a subset of nature. At date t, nature has some actions that she could take. These are her measurable subsets of actions. So take any measurable subset of actions. You can ask, conditional on the history, what's the probability that nature takes action in that set? So that's this number. We're going to say that p hat is a delta perturbation of p if the probability that p hat assigns to any such measurable set, conditional on any history, is within delta of what p would assign to that. So it's a very strong, to be delta close, you have to be delta close in probability for every measurable event for every history. Okay? So for example, right, things that we're kind of familiar with, so, if p hat were something like 1 minus delta p, so maybe put a t here, plus delta some other probability function for nature, then this p hat would be a delta perturbation. Okay, so just perturbing pt delta towards some other transition probability for nature, that would be a delta perturbation. But and that almost is a characterization, really, but it's not quite. So that's okay, fine. And same for the players. A delta perturbation of the strategy profile is simply for every player I and date t, b hat I must assign probability that's within delta of the probability that bit assigns to that measurable set of actions for player I at date t, conditional on any signal that player I at date t might observe. Okay, so that's a delta perturbation of nature's strategy, of nature's probability function, and a profile of strategies for the players. Okay. The other thing, what the game with nature's perturbed probability function. Of course, you know, when we perturb the player's strategies and we perturb nature, what does it mean to perturb nature? It means that's the game we're playing now. We're playing the game when nature is using the perturbed probability function. So we need to talk about that. There's not much to talk about. We'll just give it some notation. If nature's probability function is p, which it is originally, but we perturb it to p hat, we'll say gamma of p hat is the perturbed game. Okay, that's simple enough. Now we can give the definition. So we'll say that B, the strategy profile B, is a perfect conditional epsilon equilibrium if and only if there is a negligible set of signals in the game, n, negligible set of signals in the game, such that for any finite set of signals outside that negligible set, for every delta positive, so arbitrarily small, there are these arbitrarily small, that is, these delta perturbations, b hat of b and p hat of p, such that in the game with the perturbed probability function, the perturbed strategy profile, b hat, first of all, in that game gives every signal in the finite set positive probability, and is a conditional epsilon equilibrium. Meaning, what does it mean to remind ourselves what's a conditional epsilon equilibrium? It means that conditional on every signal event that has positive probability, every one, so including these finitely many, the players are conditionally epsilon optimizing there. Okay? So here's a fact, not so hard in finite games, Krebs-Wilson finite games, let's call them today. Those are ones where nature's finitely many states always have strictly positive probability. The strategy profile is part of a sequential equilibrium, if and only if it's a limit of a sequence of perfect conditional epsilon equilibria as epsilon tends to 0. So this concept, of course we have to take epsilon to 0, generalizes sequential equilibrium from finite to infinite games. And one can, if you really want to define systems of beliefs, you can do it. There are some issues, and the paper the paper goes through that. Back to that first example, yes, where testing by only perturbing strategies gives non-existence, but now, you know, we said intuitively perturbing nature should lead to no problem, and indeed. It is no. So there are many perfect conditional epsilon equilibria, but one example is the one that I described. Player 1 just chooses x uniformly, and player 2 always chooses y equals 2. And how do you have to check? You have to check. To check it, you have to, you know, for any finite set of signals, you have to look for perturbations. Well, it's easy here. You could just, for any finite set of signals, for player 2, you could just perturb nature to be uniform on that finite set of signals. So when you see that set of signals, you think actually it was theta 2, and so you choose y equals 2. Okay? So that's one way to rationalize this particular equilibrium that seemed okay. But you could perturb also player 1 and make the beliefs 50-50, whatever you want. And in this second example, the topological approach where that doesn't work, so this was that bad equilibrium where I was choosing uniformly, player 2, you were choosing uniformly, and we just weren't checking conditional on all the open sets. Everybody was conditionally optimizing, but we weren't checking your rationality at that critical signal S2 equals 0. Well, of course, perfect conditional epsilon equilibrium is not going to let this stand, because it says for any finite set of signals. So just take the singleton set, S2 equals 0. You must be able to perturb the strategies and nature so that this signal has positive probability. And once this signal has positive probability, player 2, in order for you to be conditionally epsilon optimizing there, you have to choose y equals 0. And once I see that you're choosing y equals 0 there, if I'm conditionally epsilon, I have to put a lot of my probability on x equals 0, and that's it. We get the subgame perfect equilibrium. So in fact, one can define subgame perfection. I won't go through, it's just what you would think it is. And every perfect conditional epsilon equilibrium is a subgame perfect epsilon equilibrium. I'll just point, of course, this ignores negligible sets of signals. So there could be negligible sets of proper subgames. So for example, if nature chooses uniform 0, 1, and you observe nature, and that happened right at the beginning of the game, that would be a proper subgame. But we don't check what's going on at, we only care there about non-negligible sets, so we're allowing you there, player 1, not to optimize. So of course we're only going to get, for all subgames outside a negligible set, we're going to get the epsilon optimizing. Okay, so that's what we mean by a subgame perfect epsilon equilibrium. If there was no nature, if there was in a game with where nature isn't present, every signal in the game, in particular every proper subgame, is non-negligible. The only negligible sets are those that are caused by nature doing something, atomless. Okay. Is there a question?
Is it the same as saying that every single outside of the negligible set you are making it an open set?
Say that again?
Are you doing something equivalent to saying that outside of a negligible set,
yes,
every singleton is an open set?
Every single is open. We're checking rationality at every signal outside an open set. I mean, if you want to define that as a topology, you can, but of course it's not going to have a countable basis. But we don't need to bring in the topological terminology, and yeah. And you can't give all of those signals positive probability at the same time, and all of that still stands. Couple of minutes. So that's just repeating the definition of a perfect conditional epsilon equilibrium. The natural thing to do here, of course, you want to take the limit now as this epsilon goes to 0. But as I said, there are examples, counter examples. If you made epsilon equals 0 here, and you wanted the players to be exactly optimizing, you'd have to get a subgame perfect equilibrium in that game that I talked about that had no subgame perfect equilibrium, an infinite game, very nice infinite game. So you can't hope to do that with the strategy profile and an ideal like conditional epsilon optimality everywhere. Okay? But what you could do is you could take a sequence of these, and by the way, I'll give you an existence theorem for this, for perfect conditional epsilon equilibrium strategy profiles. I will give you an existence theorem for that. And you could imagine looking at the path of play that comes out of a perfect conditional epsilon equilibrium for every epsilon. Taking the limit and looking at the limiting path of play, if that's something you might care about. And so that's what we call a perfect conditional equilibrium distribution. What is it? It's a probability distribution over the, remember capital A was a set of outcomes of the game. This is a mapping from measurable subsets of the outcomes of the game into 0, 1. So think about a probability measure. It'll actually be finitely additive. It might not be countably additive, but it will always be finitely additive. We can define this to be the limit. So take a net of perfect conditional epsilon equilibria, where the epsilon is converging to 0 along the net. And we can define then mu to be a perfect conditional equilibrium distribution if it's the limit in this pointwise sense, if it's the limit of the distributions that arise along the sequence, this net, excuse me, of perfect conditional epsilon equilibria. So each perfect conditional epsilon equilibrium induces a probability distribution over outcomes, and take the limit of that in this pointwise sense. And you know, one has to use Tikhonov's theorem to get existence of these limits, but that's the benefit of thinking about this as a subset of the infinite product on 0, 1. But you give up countable additivity when you do that. But in finite games, a strategy profile is part of a, now this is exact, a strategy profile is part of a sequential equilibrium if and only if its outcome distribution is a perfect conditional equilibrium distribution. Okay, so this concept, perfect conditional equilibrium distribution, generalizes the notion of a sequential equilibrium distribution to infinite games. Okay, exactly. Let me just, I'm now a bit over time, so I won't go any more slides. I actually have to give an existence. But here's a class of games we call regular projective games, where it's a fairly large class where we get existence of a perfect conditional epsilon equilibrium and conditional epsilon equilibrium distribution. So action spaces are products. Let me go to here first. Standard, this is the regularity part. Non-empty compact metric spaces. Okay, so it's what you would think. The projective part, what do I mean by this? Your signal is a projection. That's what this is saying. Okay, so this is saying that your signal, player I at date t, is a function of the history. What is it? It's just some collection of the coordinates. So it's just a projection of the entire history onto some of the coordinates of that history. Okay, that's the sets MIT are coordinates of the history for you, player I at date t. So that's what we mean by, that's the sense in which this game is a projective game. What you observe are actions taken by players or nature. If my action space itself was a vector, maybe you only observed my first coordinate and my third, but not the other coordinates. Okay. Continuous payoff functions, and then we have here the nature. We have something like the Milgram-Weber diffuseness condition, but it's actually not quite that. But I won't go into it anymore. And I'm over time, so I'm just going to leave it at that. And this is a large class of games, covers a lot of territory, covers all finite games in particular, which is not a big deal, but it's good to have that included in the theorem. And a lot of games that economists use. And let me skip that and just get to the theorem. Okay, so here's the perfect conditional epsilon equilibrium, perfect conditional equilibrium distribution. And here's the theorem in any regular projective game of the class that I just described. For every epsilon, that game possesses at least one perfect conditional epsilon equilibrium. And also, you can, once that's true, Tikhonov's theorem tells you there will then be at least one perfect conditional equilibrium distribution. And I should stop there because I've gone over a few minutes.
Thank you very much. Actually, we still have a little time before we originally scheduled.
That's true.
So we should perhaps have some questions.
Happy to answer any questions now or at lunch. Yeah, right.
The existence of conditional epsilon equilibrium, even forget about your perfect. Is it obvious?
Oh, condition? No. It's not. No, not entirely obvious, right?
This projective assumption.
The projective assumption. Let's see. Conditional epsilon equilibrium. The truth is, I don't know for sure. Let's see. The question, do you need this to be able to, for your theorem? Part of that is, are you smart enough to prove it without it? So I don't know. Do I need? Do you need? Maybe I need and you don't need, right? Certainly our proof uses that. The advantage of the projective games is that it makes the inferences and perturbing the player's strategies easy. Now, with the conditional equilibrium, there's no perturbation necessary. It's almost just a Nash equilibrium, really, right? No, Nash equilibrium is not a subgame perfect doesn't exist.
Yeah, but it's conditional also has this property of subgame.
But off the path you can do irrational things. You're only checking here on path. Conditional epsilon equilibrium only checks rationality on path. So it's essentially a Nash property, and so I'm just, it's probably the case that one could do much more generally than to check existence of conditional epsilon equilibrium. So, thanks, that's a good question.
Okay, that's probably a good moment to conclude. Many